Hello everyone. Today we will discuss about dynamic modulus of bituminous mixtures. So I'll discuss what is the need for development of a modulus called dynamic modulus, what are the test standards available, how the specimen is prepared for this test and what is the testing protocol, and finally the post-processing of this data. So as you know, in the Indian context, we design a flexible payment as per IRC 37/2018. So this is a typical cross section of payment that is given here. I have taken from IRC 37. We know that the bottom layers of the payment structure are basically unbound layers such as granular materials, and the top layer is your bituminous layer. Okay. Now when you characterize this material for the analysis of the payment, you have to consider this property of the material. So your granular material is more or less characterized as an elastic material, and you use a resilient modulus MR for the characterization of this material. Whereas when it comes to the bituminous layer, we know that it is a viscoelastic material. So we should have a property that will actually capture the viscoelastic nature of the material so that you can input it, do the analysis of the structure. As far as IRC is concerned, you use a resilient modulus value for bituminous mixtures. Now we will be discussing how the resilient modulus is captured in another lecture. Now this resilient modulus value will actually depend upon the rate of loading, the type of the mix, the binder content, the air voids in the mixture, the temperature of test and so on. But IRC actually suggests you to take one modulus value for the analysis of the structure. Say for example, your annual average payment temperature is of the range of say 35 and you are using bituminous concrete and a dense bituminous macadam with VG10 bitumen, then you have to choose 1000 MPa as your dynamic or as your resilient modulus that goes into the analysis of the structure. So how it is done is that you use the modulus value here and the respective modulus value for the granular materials and the subgrade, and you do a layer elastic analysis or a layered elastic analysis of the structure. And you will identify the critical strains. As far as a payment is concerned, the vertical strain on top of the subgrade is one critical strain, and the tensile strain at the bottom of the bituminous layer is another critical one. These are correlated to the rutting performance and the fatigue performance of the payment, which are the two major distresses that we consider for the design. Say for example, this is related to the rutting of the payment and this parameter is related to the fatigue cracking. So what is important is that the design of the layer thickness and choice of the material will definitely depend upon this analysis, which in turn will depend upon the material modulus that you provide in the analysis. So what essentially should be the characteristics of this modulus is that this modulus is a function of various factors. We know that the bituminous mixture modulus can depend upon the rate of loading. Say for example, I have a vehicle moving on a pavement surface at a speed of around say 20 km/h. It is a slow speed or the rate of loading that is or the time rate of loading that is happening on the surface is sufficiently long. In that case, the modulus of the material will be low. Whereas if the vehicle travel at say for example 80 km/h, the loading duration will be short, and in that short duration your material will behave like an elastic material with a high modulus value. So as I say, so this is what we have already discussed in the viscoelastic behavior of the material. Professor Mully has in detail discussed about this characteristic, and hence at higher loading durations you will see a lower modulus, and at lower loading durations you can see a higher modulus for the material. And second is the range of temperature at which you do this test. Say for example, your payment is under a temperature of say 20 degrees Celsius. Now your material is very stiff and it can give you a very large modulus value. Whereas when it goes to 60 degrees Celsius, your material will be less stiff and the modulus of the material will be substantially low. So your modulus depends upon the temperature. And another aspect is the aging condition. See, this aspect has already been discussed by Professor Nidita in her lecture on aging of bituminous binders as well as mixtures. what happens is that as the material ages, it becomes more and more stiff, and there could be a increase in the modulus value of the material. Some can say that this is a advantage as you go, as the material ages, you have an increase in modulus, but at the same time there is a problem that if the modulus is very high, the material is very stiff, then there are chances of failure due to fatigue cracking. Okay, so aging also has an effect on the modulus of the material, and of course your modulus will depend upon the mixture characteristics, whether you use a modified binder or an unmodified binder, what is the stiffness of this binder at these various conditions, then what is the gradation of the mix that you have used, then how much is the binder content and the air void under consideration. So all these aspects will define how much is the modulus value of the material. So in general, I can say that this modulus is something which is time dependent, and also it is temperature dependent. So such a modulus has to go into the analysis of a flexible payment. So this is what is incorporated in the mechanistic empirical payment design strategy that is developed by National Cooperative Highway Research Program. As per the mechanistic empirical payment design method, you have to determine the modulus value of the material at different loading frequencies and temperatures of interest where you are going to use this material. Now you call this modulus as dynamic modulus. So in the level 1 of MEPDG, it is required that you determine this modulus value in the laboratory. There are other levels of analysis in MEPDG as well. There is a level 2 and a level 3, which does not require you to capture this dynamic modulus value in the laboratory, but instead you can use predictive equations that are provided by MEPDG. Now another aspect is that this dynamic modulus you can capture for certain range of frequencies and temperatures, but in actual condition there could be another temperatures and frequencies that you will be that will be coming, and you can actually capture you can actually determine the modulus values at those temperatures and frequencies by using a master curve. So Professor Padma has already discussed about how a master curve can be constructed from the dynamic modulus data. This is a general framework of a mechanistic empirical payment design strategy, wherein, as I said, there could be different environmental conditions in which your payment will be subjected to. The traffic loads as well as the duration of traffic will be different, and your service life also will be different. Then comes the materials. Now, as I said, the material properties are to be identified as a function of frequency as well as temperature. In the analysis and design, what happens is that you start with a trial payment strategy, okay, and when you give all this information as what is the environmental condition, what is the traffic, and what is the time temperature dependent modulus value, when these are given to the analysis, there are payment response models which will capture what is the respective response of the material in terms of, say, stress, strain, deformation, etc. Okay. Now this is correlated to payment performance model, or these are called the distress transfer models, which will actually evaluate how much will be the distress in the field in terms of rutting, fatigue cracking, etc. And we will check whether the performance criteria is met or not. If it is not met, the strategy can be modified. You can vary the thickness of the layers, or you can vary the type of the material that is being used. So this is how the MEPDG framework is working. We are not going into the details of the payment design in this course, since we are focusing only on the material characterization in this course. Okay. So what I want to emphasize is that this material characterization for a modulus value in terms of time and temperature is necessary when you actually want to include it in the payment design. Now let me discuss what is dynamic modulus, what is its definition, and what is this phase angle. So dynamic modulus is defined as the absolute value of a complex modulus, which is calculated by dividing the peak to peak stress by the recoverable peak to peak axial strain when a material is loaded in with a sinusoidal loading in a stress controlled test. Okay, I will come to this. Now phase angle is defined as the angle in degrees between the sinusoidally applied stress and the resulting strain in a stress controlled test. Let us have a look at it. Say for example, I am applying a stress of the form sigma 0 sine omega t. So, this is my stress wave. Now, the strain will follow. Since it is a viscoelastic material, it has an elastic part as well as a viscous part. Now, the strain will lag. So, this is the strain component which is, or the strain wave, which is epsilon 0 sine omega t minus phi, where phi is your phase angle. Okay. Now, here the material is, the sample is shown as a cylindrical sample and you apply an axial compressive sinusoidal stress. Okay. Let the peak to peak stress is sigma 0 and the peak to peak strain is epsilon 0. Then this modulus value is a complex modulus which can be explained as mod E star cos phi plus I E star sin phi, whereas this is the real part and this is the imaginary part of the function. So, that mode of this quantity, which is sigma 0 by epsilon 0, will give you the dynamic modulus, and phase angle is given by Ti by Tp, where Ti is the time duration between a stress and the corresponding strain wave, and Tp is the average duration of a stress wave in seconds into 360 will give you the phase angle. Now, why we go for a Haversine or a sinusoidal waveform? Now, or what should be the waveform that will correspond to the type of loading that is happening in the field? There has been substantial amount of work that is done by, say, Richard in 1971, and in his paper, it is very clearly defined that your normal, when a vehicle passes on a pavement surface, it will follow essentially a path like this, as shown here. Okay. Now, this can be approximated as a Haversine waveform, or it can also be approximated as a triangular waveform. Okay. So, you see here that it is approximated as a triangular waveform, and in the first figure you see that it is approximated as a Haversine waveform. Okay. Now, how much should be the duration of this application? That is D as shown here. Now, this is very important. Now, there has been several studies done by him, and it is shown that this will definitely depend upon the speed of the vehicle. If the vehicle moves fast, this duration on the surface will be very small. If it's a slow moving traffic, this duration will be more. And another important aspect is that this will also depend upon the depth of the pavement where you are looking at, where you are capturing this response. Say for example, if you go deeper, as you can see from the graph provided by Richard, this is the equivalent pulse time versus the depth below the pavement surface. So, for all temperature, all speeds, if this is 15 miles per hour, this is 45 miles per hour, for in all such cases, you can see that as you go deeper into the pavement surface, this action or the duration in which the stress acts goes on increasing. And the second aspect, as I said, is depend upon the speed. So, if you have a very low speed, then definitely you have a higher pulse time, whereas if you have a faster speed, the pulse time has to be lower. Okay. So, he has actually done a layered elastic analysis to identify this, but then of course your material is viscoelastic, so he has corrected it for inertia as well as viscous effects, and these studies were correlated with the AASHTO road test, that's actual road pavement data are collected, and has come up with that a Haversine loading will very well represent the kind of load that happens in the field. So, depending upon the loading, the speed, you can have a Haversine load with the pulse distance, the pulse duration given according to the speed of the vehicle. Okay. Now, coming to the determination of dynamic modulus in the laboratory, you have different the standards set by ASTM, but ASTM D3497 was later withdrawn, and as of now there is no replacements provided for the same. Then you have AASHTO standards. AASHTO TP6014 is used for the preparation of gyratory compacted specimens for the test. And then for the determination of dynamic modulus, you have AASHTO TP79, which is later released as AASHTO T378. And for the preparation of master curves from this dynamic modulus data, you have AASHTO PP61. Okay. So, I will be discussing with respect to AASHTO TP 79. Now, first comes the specimen preparation. So, as I said, you do this test in the laboratory on a specimen of 100 mm diameter and 150 mm height. Okay. So, first you batch the aggregates for the mix that you are preparing, and then you choose the binder, and the aggregate as well as the binder has to be first heated. Say for example, aggregate heated at 170 degrees Celsius and binder at 165 degrees Celsius if it is an unmodified binder, or if it is 185 degrees Celsius for a modified binder, and then they will be mixed either in a hand mixing or you can go for a machine mixing, and then the mixed material will be short term aged. Now, you have to consider the kind of aging that is happening when you are mixing and laying and compacting the material in the field. So, as per AASHTO standards R30, you age the material for 4 hours at 135 degrees Celsius. Okay. Now, regarding aging, Professor Nivedita has already explained about how this aging happens or what are the effects of aging in her lecture. So, after 4 hours, you will take it and then heat it to around 150 degrees Celsius so that you can compact it properly for around half an hour, and this mixture will be compacted in a superpage aeratory compactor. Now, the compacted specimen will be cored and then sliced to get your required specimen of 100 mm dia and 150 mm height. Now, the air void content at which you will do this dynamic modulus test is 4%. Okay. Now, the loading is applied as a Haversine compressive loading. As I said, your dynamic modulus is defined in terms of a sinusoidal wave like this. Okay. But the problem with a sinusoidal wave is that if you have to apply a sinusoidal wave, it has to be compression tension. Okay. So, in a cylindrical specimen, if I have to apply compression tension, the test procedure will become far more complicated because you have to apply a tensile load then a compressive load. So, rather than doing it in a tension compression mode, it is actually done in a Haversine compressive load. Say it will be loaded like this in a Haversine fashion. Okay. How this is analyzed to a sinusoidal wave, that we will discuss later. Now, coming to the temperature of testing, you can test the temperature. Normally, we in Indian conditions will test from 0 to 60 degrees Celsius, whereas the MEPDG suggests that you have to start the testing from minus 10 degrees Celsius to 54 degrees Celsius. Then coming to the frequency of loading. Now, this frequency you can choose from a high frequency to a lower frequency, as I said, to represent fast moving vehicles as well as slow moving vehicles. In the simple performance test apparatus or the asphalt mixture performance test apparatus by IPC, it is possible to go from a frequency as low as 0.01 Hz to as high as 25 Hz. Say for example, you can have 25, 20, 10, 5, 2, 1, then 0.5, 0.2 and 0.1 and even up to 0.01 Hz. So, this many frequencies you can test for every temperature. Okay. Now, why this many frequencies is that, as I said, you can have traffic which is slow moving as well as fast moving. Say for example, 25, 20, 10 and all will represent the speed in a highway, whereas low frequencies like 0.2, 0.1 etc. may represent vehicles which are coming at a signalized intersection or stationary at an intersection. Okay. So, we have to consider the traffic, the movement of the traffic for the whole spectrum, and hence we have to do it at all these possible frequency ranges. And as I said, at different temperature conditions, from a lower temperature to a higher temperature. And the MEPDG suggests that you do it at different temperatures of minus 10, 4.4, 21.1, 37.8 and 54 degrees Celsius at least 5 frequencies. Now, let me discuss how this specimen is arranged, or what is the instrumentation for the testing. So, as I said, this is a cylindrical specimen. So, you have to apply a sinusoid, a Haversine stress pulse, and you have to capture the corresponding strain. Okay. Now the strain has to be captured from the specimen. You don't capture it for the entire specimen because there could be end effects on the top and bottom. So what is normally done is you connect LVDTs to the specimen at a particular gauge length in the center. Say for example 100 mm is taken as the gauge length and you connect 3 LVDTs because it's a very heterogeneous material and the response at all the directions need not be the same. So it is required that you collect responses at different locations and average it out. So you use 3 LVDTs which will be connected on specimen at 120 degrees apart. Now we have arrangements to fix this because how we normally do is that you glue nuts at 120 degrees apart on this, and onto that nuts you have, so you can see here, fixtures will be placed on those nuts and the LVDTs will be placed on here. So you see the first LVDT here and the other 2 LVDTs on the two sides. So it is at 120 degrees apart. You have 3 LVDTs which collect the corresponding strain due to the applied stress. Okay. Now you have the figure here shows the simple performance test apparatus, or now it's called the asphalt mixture performance test apparatus. You have the data acquisition system and this is a thermal controlled chamber. Okay. So inside the chamber you can keep the specimen and then you have to condition the specimen. So for that what normally is done is that either you use a dummy specimen with temperature probes inserted inside it and test how much time it will take for the entire specimen to reach the specified temperature, and you use that much of conditioning time for your test specimen as well. Okay. Now after fixing the LVDTs on the 3 sides, this will be kept inside the loading frame with the lower platen at the bottom. Then there is a friction reducing element is given, then the specimen, then again a friction reducing element and the top platen will be placed, and then the chamber will be closed, and after conditioning you can start the testing. A contact load of approximately 5% is given so that this contact between the loading platen and the specimen is not lost. And now the whole idea in this test is that you have to test the specimen in the linear viscoelastic regime, because you are trying to find a modulus in the linear viscoelastic regime where the time temperature superposition can be applied to develop a master curve. Okay. So what is required is that you have to understand like what is the stress level that will be causing a strain which is well within the linear viscoelastic regime. So several studies was conducted by MCHRP as part of the development of this mechanistic empirical method, and they have come up with the suggestion that you can use within a strain of say 75 to 125 micro strain for an unconfined test, you can have a linear viscoelastic regime, and if it is a confined test you can have the strain range of 85 to 115 micro strain. So if you are testing it within that range, your specimen will be more or less in the viscoelastic regime. And as I mentioned, you can here there is unconfined and confined test. So you can do both ways. So your material in the field, if you consider, the material is actually subjected to a triaxial state of stress. So if you want to actually represent your sample in that way, you can do it in a confined test with the confinement applied all over. So in that case, if it's a confined test, you have to cover the membrane, cover the specimen with a rubber membrane so that the pressure is applied from all around. Okay. So you apply the stress in such a way that the strain is well within this limit of say 75 to 125 or 85 to 115, say approximately 100 micro strain. Okay. MEPDG also suggests the stress levels, typical stress levels at which you can have the strain response. Say for example, if you are testing at 54 degrees Celsius, a stress in the range of say 35 to 70 kPa can give you a strain which is well within this regime. But when you are testing the sample, as I said, your temperature will affect the modulus value, your aggregate gradation, your binder content, the stiffness of the binder, and the loading rate, everything is going to affect the modulus value. Now, how do you ensure that it is well within this regime? So, this is how the test protocol goes. If you have to test a sample at a particular temperature, at that temperature you will do all the frequency switch. So you will start from the highest frequency first and then go to the lowest frequency. Say for example, you are testing it from 25 Hz to 0.01 Hz. You will go first 25 Hz frequency testing, and then immediately without any rest period you go to the next frequency of say 20 Hz, then you go to the 10 Hz and so on. Okay. So, and again in a specimen, if you are doing the test, repeating the test, you will do it for the lowest temperature first and then you will go it for the highest temperature. But if you observe that there is substantial amount of irrecoverable deformation that is happening in this test specimen, you will not use the same specimen to be tested for different temperatures. You will use a separate specimen. So, in the test procedure, say we start with 25 Hz. So, what it does is that first of all you have to provide a seed modulus, because the instrument doesn't know like what is the modulus of the value of that particular specimen and what should be the stress level to be applied. So, what is done is that first you give input a seed modulus. So, what it does is that it will calculate how much should be the stress that is to be applied, so that the strain is within 75 to 125 microstrain, and this is the corresponding modulus. So, that stress level will be first applied. So, this first is the seed modulus load cycles. So, those cycles will be applied and the data will be captured, and in real time it will capture how much is the modulus that is coming for the stress and the strain level. Okay. Now, once we realize that okay, this stress level is not going to help the strain within that limit, it will readjust the load cycle. So, the stress levels will be readjusted again so that it will represent the response of the material. Okay. So, in the readjust load cycle, so we will see another 5 cycles of readjusted load cycles. Then it will do 10 test cycles wherein the actual data will be collected for the determination of dynamic modulus. Okay. So, in every frequency it goes like this. First you have the seed cycles for 5 cycles for the seed modulus, and then 5 cycles for the adjusted value of stress, and then the actual test which will be for 10 cycles. So, this last 10 cycles will be used for the computation of the dynamic modulus. Now, say 25 Hz testing is over, now it has to move to the 20 Hz. Now, as it goes to the 20 Hz, again the material response is going to be different. We know that if your frequency is reduced, then it means that your test duration is increased. If your test duration is more, definitely the dynamic modulus is going to get decreased, or you can say that the strain levels are going to be higher. So, in that case, what is normally done is that the dynamic modulus that is obtained from the first set of tests, a 75% of that will be taken for the next frequency. So, this is the next set wherein it is taken 75% of the modulus based on the first set. Okay. So, this process will be continued. Again 5 cycles will be tried, then it will be readjusted for another 5 cycles, and then the test cycles of 10 numbers. Okay. So, this process will continue till the last frequency of say 0.01 is reached. Now, you normally test at least 2 or 3 samples for repeatability, and the data quality that is mentioned in the NCHRP report is that you need to have a load standard error within 10%. When I say load standard error, this means how well your loading wave follows this Haversine pattern. Okay, that is a load standard error, and the deformation standard error is how well the deformation wave follows a Haversine pattern. It should also be well within 10%, and then comes the deformation unity, how the deformation measured between adjacent points vary from each other. So, that has to be within 30%, and the phase angle uniformity defines how the phase angle measurements of adjacent measurements vary from each other. So, that has to be well within 3%. So, you have to test multiple samples so as to get the repeatability of results or the data quality well within this limits.